In this video, we're going to discuss what happens when we move the center of a conic section, which in the case of a hyperbola or a ellipse, we would move the center. In the case of a parabola, we'd be moving the vertex, but in either case, we're going to be moving the vertex or center of a conic section away from the origin. So remember that your center or your vertex is a point HK, okay? Now, if h is a positive number, it is going to shift the graph right. So if h is greater than 0, or the graph will shift left if h is less than 0, or if h is a negative number. If k is positive, the graph will shift up, and if k is negative, the graph will shift down, okay? Other than that, though, it's all the same rules for graphing parabolas, ellipses, and hyperbolas. So let's look at a few examples. So first, we want to find the center, foci, and vertices of the following ellipse, and then determine the lengths of the major and minor axes, and then sketch the graph. So just like we've done in all the previous videos, we're going to do our sketch as we analyze the equation, okay? So if you remember for an ellipse, to determine how it's oriented, we look for the variable with the bigger number in the denominator. So in this case, 16 is the bigger denominator. So this ellipse is going to be oriented vertically. Okay, so that means, if you remember, we're going to get some kind of ellipse that looks like that. Okay, now the center we get from these numbers that are added or subtracted to x and y. Okay, and basically what we do is we switch the sign of each of the numbers to arrive at our center. So if you remember, the original equation had minus signs in it, and so that is what causes these signs to flip. So our center will be 3, negative 2. We found our center, so let's go ahead and start graphing. So if we draw some axes here, I'm going to leave the y-axis a little longer because I know that this is going to have a vertical orientation, okay? So we know from our equation that a is equal to 4 and b is equal to 3. So this time our center is 3, negative 2. So I'm going to graph that point first. So there's my center. And from that center, I'm going to go up 4 units and down 4 units to get my major axis. So we go up 4 units and down 4 units. All right, so this is the point 3, 2, and this is the point 3, negative 6. So that's my major axis. Now my minor axis we get by going left 3 units from the center and right 3 units from the center. So we go 3 units to the left, and that will put us at the point 0, negative 2, and we go 3 units to the right. So that will put us at the point 6, negative 2. Okay, and so now we have all the points we need to graph our ellipse. So all we need to do is connect these 4 vertices and we get our ellipse. All right, so let's just find the other stuff that the directions say to find. So let's go ahead and find the foci, which first we need to find that variable c. So for an ellipse, remember c squared is a squared minus b squared. So that will be 16 minus 9, which is 7. So c is equal to the square root of 7. All right, so my first focus then, and we know for an ellipse we'll have 2 foci. Okay, the first focus will be square root of 7 units up from the vertex, and the other foci will be square root of 7 units down from the vertex. So our first focus will have coordinates 3, negative 2 plus the square root of 7, and focus 2 will have coordinates 3, negative 2 minus the square root of 7. Okay, for graphing purposes, it's okay if you get decimal approximations for these coordinates, but when you write them down like this, I would rather see the exact form. All right, So if we put these foci on our graph, the square root of 7 is going to be between 2 and 3 because 7 is between 4 and 9. So it's going to be somewhere up here for focus 1 and somewhere about here for focus 2. So I'll just call those points F1 and F2, but notice off to the side here that I labeled what the ordered pairs were. All right. Let's see, we can go ahead and list our vertices. So those are 3, 2, 3, negative 6, 0, negative 2, and 6, negative 2. So those are our vertices. We also need to find the lengths of the major and minor axes. So length of the major axis is going to be 2 times A, which is 2 times 4, which is 8. And the length of the minor axis is going to be 2 times B, which is 2 times 3, which is 6. Alright, so we found everything we need to find and we've sketched our graph. So yeah, so it's really not that different from what we did before. It's just now our center is not at the origin. Okay. So in the next example, we're looking at a parabola. So we want to find the focus, vertex, and directrix of the parabola and then sketch the graph. So the first thing you should notice about this equation is that it's not quite in standard form. So to put this in standard form, what we need to do is get y to have a coefficient of 1. So if we factor out a 2, we get x plus 2 quantity squared is equal to 2 times y plus 3 over 2. And so now our equation is in standard form. So if you notice, this equation is of the form y is equal to x squared. So that means that our parabola is going to be vertical because the x is squared, and because 2 is positive, it's going to be opening up. So this parabola opens up. All right, so we can go ahead and sketch an x and a y axis. And so let's get to finding what the vertex is. So the vertex is sort of like finding the center on the ellipse or the hyperbola. So the vertex is going to be here negative 2, comma, negative 3 over 2. And that comes from the fact that we have a positive 2 with the x and a positive 3/2 with the y. So to find our focus, what we want to do is look at the coefficient 2 right here on the right side of the equation. So we know that the coefficient of the equation of a parabola in standard form is equal to 4p. So we know that 2 is equal to 4p. Okay, so what this tells us, if we divide both sides by 4, is that p is equal to 1/2. So what this means is that the focus is 1/2 unit away from the vertex, and the directrix is 1/2 unit away from the vertex. Okay, so let's go ahead and start graphing these points. So the vertex is negative 2, negative 3/2. So I'll go 2 units to the left, and I'll draw 2 units going down, but we'll only plot it in between those 2 units. Okay, so this is our vertex V. Now our focus is going to be 1/2 unit above the vertex because our parabola is opening upwards. So our focus is going to be the ordered pair negative 2, negative 1, because if we add 1/2 back to negative 3/2, we'll end up with negative 1. So our focus is right above the vertex, about right there. And I'll label that point F. Okay? And so if we draw a rough shape of an upward opening parabola, we get something that looks like that. So the last thing we need to put into our picture is the directrix. So the directrix, as I said, is going to be 1/2 unit below the vertex because it's in the opposite direction of the focus. So we might put a starting point right there for the directrix, but we know that that's actually going to be a line. And remember to draw it dotted because it's not really a part of your graph. So we're going to draw a dotted line at y is equal to -2. So the directrix, remember, is a line, so we write that as y equal to -2. Okay, so while we do graph this little point right here, that is not actually our directrix. The directrix is the entire line. All right, and so now we found the vertex, the focus, and the directrix. So we've already got the graph sketch, so we're done. That's it. Okay, so one last example we're going to look at for shifted conics is a hyperbola. Okay, so remember, with a hyperbola, the orientation depends on the positive term, not the denominator. Okay, so in this case, you notice x is the positive term, so this hyperbola is going to be horizontal. All right, now a in this case is equal to 2 because 2 is the square root of 4. B is equal to 3 because 3 is the square root of 9. So we can start drawing a graph. Oh, let me get the center. So the center is going to be -4, +1. Okay, and we find that center the same way that we found the center for the shifted ellipse. You're just looking at the number that's added or subtracted from x, the number that's added or subtracted from y, but to get the coordinate, you basically just switch the signs. Okay, so let's start drawing our picture. So we have a y-axis and an x-axis. Now because a is 2, well first let's get the center. So we go to the left 4 units and up 1 unit. So that will be our center. Okay. A is 2, so and it's horizontal. So from the center, we want to go 2 units to the left and 2 units to the right. So that will put us here and here. So this point is -2, 1, and this point is -6, 1. Okay. For the other sides of our box, to get those points, we look at b equal to 3. So up from the center, we'll go 3 units up. So that will put us about right there. And that's the point -4, 4. And we also need to go 3 units down from the center. So if we go 3 units down, we end up right there. And that is the point -4, -2. Okay, so let's go ahead and draw in that dotted box. That's going to help us get our asymptotes. Okay, so there's our box, and so now we can get our asymptotes. And remember, that's just connecting the corners of the box through the center of the hyperbola. So our first asymptote might look like that, and the second asymptote looks something like this. Okay, now because our hyperbola is horizontal, the points that we're going to use as vertices will be the ones on the left and right sides of the box. So this will be a vertex, and so we can draw a curve to approach those asymptotes. And we can do the same thing on the left side. So we can draw our curve there through that point and approaching both asymptotes. Okay, so our vertices are the points -6, 1 and -2, 1. All right, so now let's find the foci. So the foci, remember, we need to find that variable c. So c, in the case of a hyperbola, we have c squared equal to a squared plus b squared. So we have c squared equals 4 plus 9, which is 13. So c is equal to the square root of 13. So the foci in this case, we're going to add that square root of 13 to the x-coordinate of our vertices, or sorry, the x-coordinate of our center, because our hyperbola is horizontal. So the foci points, I'm going to call F1 and F2. F1 will take the center and will subtract square root of 13 from the x-coordinate, but the y-coordinate will stay the same. For the second focus, we'll add the square root of 13 to the x-coordinate, and the y-coordinate will again stay the same. So these foci will be somewhere around here. So this might be F1 and this might be F2. Okay, so those are our foci. We found our vertices, so let's just get the asymptotes. Okay, so just like with the center at the origin, the center is still the one point that's contained on both asymptotes. So when we write our asymptotes in point slope form, that's the point that we're going to use to help us get the equation of a line. So point slope form, we have y minus 1 because that's the y coordinate of our center. So these are asymptotes. And that's going to be equal to some slope times x plus 4. So we have x minus the x coordinate of the center, so that would be x minus a negative 4, which is x plus 4. Okay, so the last thing we need to do is just find the slope. And you can do this the same way we did in the hyperbola video, where we looked at the rise over run from the center to the corner of the box. So if we go up from the center, we're going up 2 units. No, sorry, we're going up 3 units. We're going up 3 units and over 2 units. So our slope is going to be 3 over 2 in both a positive and negative direction. Okay, so our slope is 3 over 2, so our asymptotes are just y minus 1 is equal to plus or minus 3 over 2 times x plus 4. Okay, and that's everything we needed to find, and our graph is sketched. So that is it for shifted conics. Now what we're going to talk about is a different form of the equation of conic sections called the general form. So the general form of a conic section that we've talked about so far is as follows. So we have ax squared plus cy squared plus dx plus ey plus f is equal to 0. So you might be wondering why we skipped the letter b, and my answer to that is we will talk about that in our little bonus lesson, which I'll put a video up for. And for the test, you won't need to know too much from that lesson, mainly just know how to classify conics, but we'll talk about that later. Okay, so anyway, we're skipping b for now. Putting a b in there makes this a lot more complicated. So this big equation right here can either represent a conic or what we call a degenerate conic. Okay, so in the case where we get an actual conic section, we can actually distinguish what type of conic we have by examining the numbers a and c. Okay, and these are the coefficients of the squared terms. Okay, so our first case is we will have a parabola if a or c equals 0. And you can think about why this is true, because if either a or c is 0, then that means we only have one of either x or y that's being squared. And so that's exactly what happens in the equation of a parabola. So that makes sense. Our second case, we could have an ellipse if a and c have the same sign, but a is not equal to c. So a and c have the same sign, S-I-G-N, but a does not equal c. Okay, and you can think about why this makes sense, because if a and c are both positive, then you've got something where you have x squared plus y squared, and that brings the equation of an ellipse to mind. Now if a does equal to c, then you have a circle. Okay, so remember in the ellipse video we said that a circle is basically a special case of an ellipse, right? And thirdly, we have a hyperbola if a and c have opposite signs. And that also makes sense, because if you think about the equation of a hyperbola, you have one term that's negative, one term that's positive, so it would make sense that your squared terms in the general form must have opposite signs. Okay, so those are some easy ways to tell what type of conic section you have without really having to do any work. You just examine the coefficients. Okay, now the problem with it, though, is that sometimes it may look like you have a conic section, but you really don't. And so the way that we actually figure out if we have a conic section or not is we have to complete the square to change the equation to its standard form. And so the standard form are those forms that we've talked about in all the previous videos of lesson 9. Okay, and doing this will actually reveal to you, as I said, whether you have a conic or a degenerate conic. So a degenerate conic is an equation that turns out to either be intersecting lines, a point, or it could be no graph at all. So again, these are equations that look like they could be conic sections, but once you get it into standard form, you realize that, oh wait, this doesn't exactly look quite right. And so even though it looked like a conic in general form, it's not really a conic at all. And so this might be an actually pretty good test question maybe. So I think I talked about a few test questions before, but I'll have on the study guide probably a test bank sort of theory questions that I could put on there, and this would be one of them. Okay, so we're going to determine either the conic or the degenerate conic by changing the equation to standard form. So you should have actually done this before with circles. So if you remember from Math 113, you should have talked about changing circle equations from the general to the standard form. Okay, and this is no different. All right. So in the first equation, we have x squared plus 4y squared minus 8x plus 16y plus 16 is equal to 0. Okay, so the first thing you want to do when you're changing this to a standard form is get all of your x terms grouped together, get all of your y terms grouped together, and get the constant on the other side of the equation. So I'm going to get all my x's together. So I have x squared minus 8x. I'm going to get my y's together, so I have plus 4y squared plus 16y, and I'm going to get that positive 16 on the other side of the equation, and it's going to become a negative 16. Okay, so that's the first step. Now what you want to do is actually complete the square. Well, first, make sure that you don't have a coefficient on x or y. So because we have a coefficient on y, we have a 4, we need to factor that out of all the y terms. So we get x squared minus 8x plus, I'm going to put this in parentheses for reasons you'll see in a second. So if we factor out the 4, we get y squared plus 4y. I'm going to leave a space there as well, and that's equal to negative 16. Okay, so now we actually want to complete the square. And the way you complete the square is you look at the coefficient of the linear term, so where the variable is raised to the first power, and you want to take that number, half it, and square it. So negative 8, we can just say positive 8. So 8 divided by 2 is equal to 4. And if we square 4, we get 16. So the number we're going to add to the x's is 16. And whatever we add on one side, we also have to add on the other side. So I'm also going to add a 16 to the right side. Okay. For the second group of terms, we have 4 as the coefficient of our linear term. So we'll do 4 divided by 2, which is 2. So 4 over 2 is 2. And if we square 2, we get 4. So 4 is the number we're going to add to the y terms. Now, because we have this 4 factored outside, what we're actually adding to those y terms is a 16. So on the right side, we're going to add a 16 rather than a 4. Okay? And so now we basically have everything we need. So what we need to do next is just simplify everything. So that means factor the left side and add everything on the right side. So on the left side, this will factor to x minus 4 squared plus 4 times y plus 2 squared is equal to 16. So negative 16 and 16 cancel. We're just left with 16. So the only thing I have left to do to get this into standard form is just divide every single term by 16 so that I get the one that I want on the right side. So my equation in standard form is x minus 4 quantity squared over 16 plus y plus 2 quantity squared over 4 is equal to 1. And so now that we have this in standard form, you can see that this conic is an ellipse. Okay, so let's go to the second example. So right away, you might notice that we only have one term that is squared. So this is probably going to be a parabola, but we need to make sure that it actually is a parabola and not one of those degenerate conics. Okay, so this time we only need to complete the square and the y's. So let's get, so this time, since I'm suspecting it's going to be a parabola, we're going to keep the y terms on the left side, and we're going to move everything else to the right side, like that. Okay? Now, because I have a coefficient on y squared, I need to factor it out of all of the y terms, so I get 3 times y squared plus 4/3 y, I'm going to leave a space, is equal to negative x minus 7. Now I need to figure out what's the number that I need to add to both sides of my equation. So if we take 4/3 and we divide it by 2, we're going to get 2/3. So we get 2/3, and if we square 2/3, we get 4/9. So I'm going to add 4/9 to the left side, and because I have a 3 sitting outside, I'm going to add 3 times 4/9 to the right side. So I have, let's see, that would be 4/3, so I'm going to add 4/3 to the right side. Okay? So now what I can do is factor down the left side and simplify the right side. So I get 3 times y plus 2/3 quantity squared is equal to negative x, and let's see if we get a common denominator there. I think it should give you negative 17/3. Okay, so we're almost done. So for a parabola, remember that the coefficient that's sitting outside here needs to be on the linear side of the equation. So right now we have it on the y side, which is squared. We want it on the other side so that it will be in standard form. So to do that, the first thing I'm going to do is just factor out the negative from this right side. So we get 3 times y plus 2/3 squared is equal to a negative times x plus 17/3. Okay, and the last thing I want to do, like I said, is just divide the 3 over. So our equation is y plus 2/3 squared is equal to negative 1/3 times x plus 17/3. Okay, and so that indeed is a parabola, just as we predicted. Okay, so in this last example, you might be like, well, we haven't seen a degenerate conic yet, so maybe this one will turn out to be one. So let's see. So I might suspect that this is a hyperbola because I have an x squared, I have a y squared, but I have a minus sign. So I'm going to suspect that this is a hyperbola until it shows me something otherwise. Okay, so first we want to get all of our x's together, all of our y's together, and move the constant to the other side. So we have 16y squared plus 64y minus x squared plus 2x is equal to negative 63. Okay, so now we want to factor out any coefficients from the squared terms. So we have 16 times y squared plus 4y, and I'm going to leave a space for that number we're going to add. Factor out the negative from the x's, so we have negative x squared minus 2x, again I'm going to leave a space, and that's equal to negative 63. Okay, so now I need to figure out what numbers I can add to the y terms and add to the x terms. So in the y's, I have 4 as my linear coefficient, so if I divide 4 by 2, I get 2, and then if I square 2, I get 4. So I'm going to add 4 to my y terms, and so I'm actually adding 64 because I have that 16 sitting on the outside. So on the right side of my equation, I'm going to add 64. To my x's, my coefficient of the linear term is 2. So if I have 2, I get 1, and if I square 1, I get 1. So I'm subtracting 1 because I have a negative sitting outside. So I'm going to subtract 1 from the right side. Okay? So that one might be a little more difficult because we're dealing with a lot more coefficients, but just, take your time, work through it, it'll turn out fine. Okay, so now all we have left to do is just factor the left side and simplify the right side. So we get 16 times y plus 2 quantity squared minus x minus 1 quantity squared is equal to, so let's see, 63 and 1 is 64, so we have minus 64 plus 64, which is 0. Okay, so here is where our problem sets in. So now we have 0 on the right side, so there is nothing that we can divide by 0 to give us 1. It just will not work. Okay, so this is a case where we have a degenerate conic. Because even though the general form looked as though it would give us a hyperbola, we actually found here, once we simplified it, that there's no way to get a 1 on the right side. Okay, so let's figure out what this actually is. So let me start with what we already have. So we have 16 times y plus 2 squared minus x minus 1 squared is equal to 0. So let's see what happens if I move the x minus 1 squared to the other side. So I have 16 times y plus 2 squared is equal to x minus 1 quantity squared. Okay, so let's divide the 16 to the other side and see what this does. So we have y plus 2 squared is equal to 1/16 times x minus 1 quantity squared. Now what happens if I square root both sides? Well, I get y plus 2 is equal to plus or minus 1/4 times x minus 1. So now, even though it was a little disguised, this might look kind of familiar, maybe like something we saw in the hyperbola video. So while it's not a hyperbola, it is the equation of two lines that intersect each other. So it's almost like the equations of the asymptotes of the hyperbola. But in this case, we're not dealing with the asymptotes, we're saying that that is the graph. So what we have here are two intersecting lines. Okay, so if you were to graph this in a graphing calculator in that general form, it wouldn't give you a hyperbola, it would actually give you two lines that cross each other. Okay, so this is a good example of a degenerate conic and how that arises from the general equation. Okay, so the last thing that we're going to do in this video is just practice classifying conics from the general form without actually doing any work. So I'm already telling you that all of these are not degenerate conics. You know that they are going to turn out to be either a parabola, a hyperbola, or an ellipse. So we're just going to assume that and analyze the coefficients and see what we get. Okay, so in example A, you'll notice that we only have one squared term. It's the 4x squared. Okay, so right off the bat, parabola. So if there's only one term that's squared, you have a parabola. In example B, notice we have two squared terms. We have a 4x squared and a y squared, but there's a negative sign between them, so they have opposite signs. So this is going to be a hyperbola. Okay, so two squared terms, opposite signs, we have a hyperbola. In example C, again, we have two squared terms, but we have the same sign. So they're both positive, so right off the bat, we know an ellipse. Okay. Example D, we still have two squared terms, and they have the same sign, but notice that they both have a coefficient of 4. Okay, so what this tells us is that we have a circle. So it's very close to an ellipse, but it's kind of like an ellipse that's symmetrical in the vertical and horizontal directions. So you can see, you can kind of picture in your head how that would turn out to be a circle. And finally, for the last example, notice the only squared term we have is the y squared. So again, that is going to be a parabola. All right, so that is a start on shifted conics as well as the general form of a conic. If you have any questions, please let me know. but that should finish you out on all of the topics you need to know to do your homework. And in the next lesson, we're going to talk about what happens when you add the b term into the general form of a conic. All right, and that will be our last lesson for the semester.